Hello and welcome to this session where we're going to discuss the film theory. So we've been developing the material balances that describe the variation of concentration across some space, across some geometry, and as we've mentioned several times, to solve that concentration accurately and correctly, we need to specify the boundary conditions. That's because our general balance only tells us how changes are related to each other, how changes in time and space are related to each other. And in order to nail down our solution, we have to provide specifics about the behavior of the solution in specific regions, either at specific instants in time or specific points in space. So related to that, we've been discussing some boundary conditions that related to the problem of interest. So for example, in the very first case study, we were talking about the diffusion of component A in a compartment through a permeable membrane. So we have two compartments and there's a concentration difference between the two, and the concentration difference drives a certain transfer of A through that membrane and eventually all equilibrates. Now, this was an oversimplified picture, right? When we describe a membrane here, we've drawn the concentration as if it's a continuous value. So the concentration just to the left here might be 20, and then the concentration just to the right is 20. Well, that's not always the case. It's typically the case that when we are diffusing into a different phase, that there is a discontinuous jump between the two. And perhaps that's harder to believe in the case of a membrane, but if you think about a gas and a liquid, let's say this was a gas and let's say this was a wetted wall, so this was a liquid film sitting on a wall, then we know that there's going to be a concentration difference here, that the concentration in here will be approximately 1,000 times greater than the concentration here. So that's just in terms of differences in density between gas and liquid. So we can see that there is a discontinuity in the concentration, and we typically model that using an equilibrium constant. So we say that there is a relationship still between the liquid phase concentration and the gas phase concentration, and we can relate those two using some correction factor, and we call that the equilibrium constant. Now, it's important to note here that these two quantities are still related. It's not the case that if your concentration changes in this liquid film, that won't impact on the concentration in the gas phase. And it shouldn't, right? If we think of it, if the concentration here changes, then that's going to change the mass transfer flux, and it's going to change the local concentration that develops just next to that liquid film. So we note here that this relationship does respect that any changes on the one side will result in a change on the other side. So that's one thing we can say. So this is easy to understand and believe in the case where we have clearly two different phases. So a gas and a liquid, we know that there are magnitude differences in the concentration, but then there does still exist a relationship between those. Now, the situation is slightly different if the difference between these phases is not so clear. So if this is a membrane, let's say it's a porous membrane, and when we say pores, we obviously mean that there are, when we say porous, we mean that there are pores in this medium. So there are pores here, and that means that if this, for example, is a gas, then in the pores, the concentration is going to be the same as the concentration in the gas in the pores. However, there's also solid material. So you have empty pores and you have solid material. So you can say in principle then our concentration here in terms of all this material is lower. So even though in the pore, in the gas in the pore, the concentration here may be the same as the concentration there, because there is less gas here, because part of this volume is filled with the solid part of the porous medium, then those parts of the volume won't contain any of the diffusing component. And if that's the case, then overall you have a lower number of moles of the component in the space. And then that also means in terms of moles per volume of the space, you have a lower concentration. And it may also be the case that this medium, that this porous medium, that the solid part also offers some additional resistance. So it might be that due to electrostatic repulsion between the molecules here and the pore medium here, that there is some additional resistance or even additional promotion of transfer. And so we have to respect that the equilibrium between this phase and this phase is not a trivial thing, that we need to know the correct equilibrium constant there. So we make no assumptions about that, right? We can no longer assume that this is just a continuous variation here in component A. So instead, we modify our expectation and our understanding to say that across an interface where we have a difference in medium, that there exists a discontinuous jump between the two concentrations, and we need to have an equilibrium constant to determine the one from the other. So let's say we happen to know the concentration here, then just with the equilibrium constant, we could determine the other concentration. So there exists a discontinuous jump here. So equilibrium, that's the first important piece to understand in this overall picture. Now the other thing to take note of is that we have some concentration variation here due to the diffusion driving force. And just to come back to this, there's no diffusion issue here. When we talk about this discontinuous jump, this is not due to diffusion differences. This is just due to the other phase being able to pack component A in a different way. So in this gas phase here, the molecules of A are packed in a certain density, and then in this other phase, component A can only pack in a certain density. So there's a difference in the densities or the concentrations that can ever be achieved in the other phase. So this is only about that. It's not about diffusion. Right, diffusion is driving force, concentration difference driving force based. And so when we talk about the diffusion rate, there's one diffusion rate that occurs here, and there's another diffusion rate that occurs there. I will say later on, we will talk about estimating a diffusion, a diffusivity in the other phase if we know if we know the diffusivity in the first phase. So there sometimes is a relationship. But for now, generally speaking, let's just accept that the diffusivity is different in the two phases. So that then determines how quickly this concentration profile is going to develop. So that's the first thing to note, your discontinuous jump, then your diffusivities in the two phases. Now, we know that the driving force for mass transfer is the concentration difference. And you see, by concentration difference, we mean the difference away from the equilibrium value. So at equilibrium, if these two are at their equilibrium values, then there's actually no driving force for mass transfer. And I'm just going to sketch that quickly. So let's say that's our interface, and let's say on the one side we had a concentration here, and on the other side we had a concentration there, and let's say those were at equilibrium. So if they are at their equilibrium values, then there's no net driving force that can be applied, and we can have flat gradients after that. So it's already at equilibrium, and just due to phase differences, there is a difference in concentration, but that's the equilibrium concentration value. So if you are at equilibrium, there is no net driving force. Even though there is a concentration difference, this concentration is effectively the same as that concentration once you correct for phase difference. So if that's the case, then there's no net driving force, and you can happily have the two fluids existing at these two concentrations for all time. And if you think about, again, if it was a gas phase, so let's say you had a gas phase here, and you had a liquid phase there. So if this was liquid, well, I should draw it more closely packed. So let's say this was a liquid phase here. Then, of course, you've got, we can easily agree that there can exist a specific concentration which is just the same everywhere in the liquid, and there's a specific other concentration in the gas that's just staying constant with time. Now let's say we somehow increase the concentration of A in the other phase. So we manage to force a higher concentration in this gas here. So let's just draw it up here, or let's use a different color. So we've gone and forced a higher concentration up here. Now we are no longer at equilibrium. So this value is not in equilibrium with this value. So that's going to drive a net diffusion into this other phase. So our new equilibrium, right, there does exist an equilibrium value with this value, and let's use this color. So you've got a new equilibrium that exists at this point now. So that means immediately next to this interface, this new concentration will cause there to be a different concentration, right? If this point equilibrates with this point, right, across this interface, these 2 points immediately next to the interface, they have to be in equilibrium all the time. So we've forced now a new concentration at this point in this liquid phase. And this new value is different to the value that was in that liquid phase. Right, so we are not talking about a separate situation now. We are imagining the case where we started out at t equals 0 with these two concentrations, and they were equilibrium concentrations. And then at t equals 0, we step increased the concentration in the gas phase. And you might do this easily, for example, just by increasing the pressure. So you've got a new higher concentration here, and then that's going to cause there to be a higher concentration immediately next to this interface. Remember, the interface is a zero volume thing, right? We only draw a line here with a certain thickness, otherwise we couldn't see it. But in nature, there's a zero volume here. An interface has no volume. So that means we have to be immediately at equilibrium on the opposite ends of this interface. And so now we have a certain concentration in the liquid phase at the interface, which is different to the bulk concentration in that liquid. So we have a higher concentration than the bulk concentration. That means there's going to be a net diffusion from this point into this liquid. And that might happen at some short time after we've increased the gas phase. And then as time goes on, that is going to penetrate the rest of the liquid until the liquid reaches its new equilibrium. So this line and this line is the new equilibrium that we would reach there. Right, so that's the concept of equilibrium. And we note here also that these profiles can develop, right? So across this interface, there may be applied certain concentration differences, which, if they are not at equilibrium, are going to force there to be gradients in the bulk. So this also introduces the notion of a bulk concentration. So you have this phase, so you've got this mass of fluid in here, and that's true on both sides. So you've got a mass of fluid here and a mass of fluid here. One is gas, one is liquid. And we can identify a bulk concentration, which means a concentration that's far away from the point of the interface. So you can say here, this is a concentration in the gas in the bulk, so Ca gas bulk. And likewise, we could identify in the liquid phase that there's a certain other bulk concentration. So Ca in the liquid, a bulk concentration. So there's a bulk concentration, and so differences in the interface, right? A different concentration near the interface when compared with the bulk is going to cause a net mass transfer flux between the interface and the bulk of the fluid. And so this is summarized here. So this is a situation where our concentrations are not at the equilibration. They are not both at equilibrium. And well, these two numbers might be at equilibrium, but the bulk of the fluid is not yet at the same equilibrium value. So if there's a difference between the bulk concentration and the equilibrium value there's going to be some gradient that's going to develop over time. And if we leave it for long enough, if this value remains fixed there and we leave this long enough, then this is eventually going to penetrate all that phase, and it's going to flatten out. And likewise here, so we have some gradient, and there's going to be a net mass transfer here. Okay, so bulk concentrations, the equilibrium concentration, those are some of the concepts here. In terms of the notation, you can see I'm also talking about x equals 0 minus, so the points immediately to the left of x equals 0, and x equals 0 plus the points immediately to the right. So there's a discontinuity, and so that's why we have to be so specific about that. Okay, so that's actually what happens. And now we want to introduce this notion of the film. And what we're trying to do there is simplify this picture. So as engineers, if we say, well, look, I realize that this kind of variation is happening, and I respect that if that I can go ahead and write a mass balance here. And I know I'll get something like dc dt equals diffusivity times d2c dx squared. So I know I can write the diffusion equation here. However, I don't want to deal with that right now. I would like to just simplify this picture down to a nice easy form for me to work with. And so if we say that, then we can realize that the difference in the concentration here, the difference between the interface equilibrium concentration and the bulk concentration, that variation, that difference, this is likely to happen over a very small region, right? This transfer, this transition, we can think of this as a small transition zone. So maybe this compartment is 1 meter long. And this only happens over a space of perhaps millimeters. Then we say, look, I don't want to spend so much of my modeling effort and my computational expense. I don't want to spend so much just on capturing this little film here. And in fact, I've revealed the name. So we think of this as a little film where all this concentration difference is occurring. I didn't want to say concentrated there. But all the difference is in this little zone. And so instead of respecting this kind of profile, we say, can't we just approximate it with a straight line difference here, where we've got the bulk concentration here, we've got the interface concentration there, and so we've got a difference between those concentrations, and there exists some there's some width here, so there's some distance here, and then we could just take the difference here and divide by that distance, and then multiply by diffusivity or some constant, and then we're done. Then we've accounted for all this mass transfer. So that's what we do in film theory. So the film is an imaginary thing. right? In nature, there doesn't exist some imaginary interface where we say, oh, the concentration was varying linearly, and then it's the bulk value after that. So there doesn't exist a line like this in nature. This is just our proposal for where we think most of the difference occurs. So the film is an imaginary or a theoretical film. And so we are saying we would like to write a nice, easy expression like this. We would like to take the difference between the interface and the bulk, so that difference multiplied with some constant. And we just go ahead and call it a mass transfer constant, or the mass transfer constant. So we would like to simplify our molar flux expression. So we are trying to get away from that gradient-based expression, from the fixed law expression, and we want to just write it in terms of a concentration difference. And there's nothing wrong with that. We are just proposing to find an alternate form like that. Now, the best way to start working with a proposal like this is to compare that with what we currently have. So we know, according to our rigorous definition from fixed law, that this is actually what happens. So this is according to our understanding, this is what we should be writing. So let's try and compare these two and develop the equation and see what that means. So if we take this form, and if we try and approximate it, right? So if we've said we are concerned with just this difference across the whole space, then we can say that this gradient can be estimated from just 2 points here. So we know it's this concentration minus this concentration, and then we can define this thickness to be delta, lowercase delta. So that's what we do here. So we say, if we are trying to find a similarity between this proposal and this more rigorous view, then the right-hand side needs to change. So we need to write an approximation to this right-hand side. So we can approximate this gradient specifically as the difference in concentrations divided by the distance traveled, right? So it's a straightforward approximation to this gradient. And now if you compare that with this form, right? So taking this side of it, so I'm just bringing that down here, and then of course this is the molar flux, and our proposal is here. So we are hoping to find a form like this. So if you compare these two equations, you can see the concentration driving force is the same. So it's Ca2 naught minus Ca2b. So it's the same difference, just there's a minus sign here. And so when we look at this, we can say, well, we can cancel these two and write simply that our mass transfer coefficient is our diffusivity divided by the film thickness, right? So that's a nice relationship then. It tells us that if we want to form a nice, easy approximation, we just need to take our existing diffusivity and divide it by the film thickness. So that's nice because we've invested a fair amount of time into estimating this diffusivity. So we know at least we have some nice correlations which we can use to estimate this number. However, there is this unknown number here, this delta. And in fact, this delta is not such a straightforward thing, right? Because you see, actually what's happening here is a continuous variation in concentration. And in fact, because of the differential nature of this of the transfer, what you find is that you never actually reach the bulk concentration, that it takes an infinite distance to reach the bulk value. So just refer to your comments from earlier about the time taken to reach equilibrium and so on, right? So because it's concentration difference based, right? The driving force is based on concentration differences. As the concentration difference gets smaller and smaller, it becomes harder and harder for any flux to happen. So it takes an infinite distance to reach this bulk value. So in fact, if you look at it that way, your film is an infinite film. Your film goes right to the end of the compartment and in fact beyond. So it looks like that's a nice, it would be nice if we could do that, but it's starting to look impossible because the film looks like it never ends. However, we are saying here, look, for all practical purposes, if you look at the exponential nature of what's happening here, that by the time you reach some distance here, there will only be a very small change afterwards. So we can simply specify a cutoff value. So we can specify that the thickness of the film is defined to be where the concentration reaches a value which is 99% of the bulk value. So we can define the bulk value. So we know that we fed the reactor with a certain number of moles and there's a certain volume. So there does exist some average value. And we can say that the distance away from the interface where we reach 99% of that bulk value, that we define to be the film. Right, so we define this film kind of implicitly. We can't say it's going to be exactly the bulk value, but it's at least 99% of the bulk value. And so once we do that, then we do get a reasonable value for delta. And so it's fairly easy then. We have a nice criterion for finding delta, and then that establishes a nice relationship between the mass transfer coefficient and the diffusivity. And in fact, we can solve for delta quite rigorously with our nice new criterion. So if we go back to our original development for the molar flux, right? Remember, this was our original form. And if we take the case where A is diffusing through stagnant B, if you go back and have a look at it, excuse me, if you go back and have a look at it, we found that it had this solution. So do go back and just check for stagnant B, that means NB equals 0. Then you take the Na across and then you solve the equation, then we had this form. Now we can rewrite it like so, and we can say that Ya equals 99% of the bulk value. So we know the bulk value and we just stick 0.99 times that in here. And then that gives us a number, and then that's another number. Everything here is defined. And so we can solve this so that we get x minus x naught. So we solve this to get our distance away from the interface. So the difference between this distance and the interface distance, that's our delta, right? And so we can estimate the delta just by solving this equation, and we'll in fact do some examples like that in the tutorial. So we can solve for delta quite rigorously in this case, and so we can estimate Kc. Now be careful with this. You can't always do this, right? In this situation where you had component A quietly diffusing through a stagnant B, then you had a nicely behaved system that had this expression and so on. In reality, in real chemical process units, there are many other things going on. So, for example, you might just stick a big stirrer in and be agitating that fluid. And you can imagine that if you are agitating that fluid, if you are mixing that fluid up, right? Let's say on this side, well, I guess we were calling it the gas. So if you were agitating the fluid here, if you were mixing this fluid vigorously, then you are causing the bulk value to get closer and closer to the interface point. So it's not that the agitation is going to disrupt the interface, but because you are stirring the gas well enough that you are shifting the position of the film. It's not that we are necessarily completely destroying the film. It would take an infinite amount of energy to overcome the difference in concentration here, but we are at least shifting the film location. And you might say, well, doesn't that just completely violate all this development? And yes, it does. That's because this same equation no longer applies. So if you are adding agitation, then the convection is not only determined by the molar fluxes here, it's also influenced by the energy that we put into the system. So that means your film thickness depends on other factors, so things like the agitator speed and so on. So that's why you'll find in the literature, it's not the case that everybody just goes and solves the mass balance and then they announce the film thickness. So in the literature, you'll find thousands of papers where people are estimating the mass transfer coefficient for their specific situation. So they know, yes, I've used a stirrer with where I've put in maybe it's a 200 watt stirrer, and in fact it goes into some crazy level of detail. So the blade angle and all the geometry specifics go into estimating the delta. So all the other factors. Right, you can imagine it's not just about the stirrer itself, it's how big is the compartment and all those things. So there may be a lot that goes on to estimate this delta. And in fact, we don't really estimate the delta, we just go and correlate for Kc. So that's just a comment that this is how you can do it for this well-behaved system, but you'll often find that it's not done that way, and that's because there's a lot more going on usually than just these kinds of processes. We will cover later on in the course under dimensional analysis some of the correlations that we can use to estimate coefficients like this one. But overall, that's the point of film theory, right? With our film theory, we can simplify our expression for the molar flux, and this is for the molar flux near the interface, right? Of course, the molar flux in the bulk of the fluid, that's a different matter, but at least here we can now start thinking about simpler expressions, and that's going to help us in developing the boundary conditions, and that's going to be the topic of the next session.